Okay, so we're here. We're doing Chapter 7 of Connecting Networks, which is talking about network evolution, so sort of where it's come in the recent past and where it's going in the close future, also the thoughts are. Anyway, so we're going to look at the Internet of Things, we're going to look at the cloud and virtualization, and we're going to look at network programming. Okay, so Internet of Things. So it's predicted that the internet will interconnect 50 billion things by 2020, this year. Using existing and new technologies, we are connecting the physical world to the internet. It is by connecting the unconnected that we transition the internet to the Internet of Things. And so basically a lot of it's about sensors and how you can get data into your systems. That's mostly what it's about, of course. All right, so the converged network and things. So dissimilar networks are converging to share the same infrastructure. This infrastructure includes comprehensive security, analytics, and management capabilities. And so the connection of the components into the converged network that uses IoT technologies increases the power of the network to help people improve their daily lives. And so basically you've got the converged network, and so then you can run all of these systems through it. So, heating and ventilation, telephone, will control electricity, data, video, physical security. So there are 6 pillars of the Cisco IoT system. And so it's got network connectivity, fog computing, security, both cyber and physical, data analytics, management automation, and application enablement platforms. And so we'll go into some of those in the coming slides. So the fog computing pillar, so you're probably thinking, what the hell's that? Well, I suppose it's sort of like a cloud that's nearer to you. And so the IoT network model identifies a computing infrastructure closer to the network edge, as opposed to the cloud could be on the other side of the planet. And so I suppose that's why they're calling it the fog. And so edge devices run applications locally and make immediate decisions. Data that does not need to be sent over the network connections, enhances resiliency by allowing IoT devices to operate when network connections are lost, and enhances security by keeping sensitive data from being transported beyond the edge where it is needed. And so you can have a client-server model, and so you've got your servers here, and then of course you may well have your sensors on the others, and so a cloud model of course is where you connect into the cloud over a distance, or of course the fog is where you've got things a lot closer. And so of course they're saying that the fog is more secure because you have it on your local network, and so some of your sensitive data doesn't have to go to the internet, which sounds like a good idea to me. All right, so there's the security pillar as well, and so of course IoT and security need to go hand in hand, even if they often don't. And so IoT introduces new attack vectors not typically encountered with normal enterprise networks. And so the cybersecurity solutions include operational technology specific security. So basically it's a hardware and software that keeps power plants running and manages factory process lines. You've got network security, so it includes network and perimeter security devices. And then you've got physical security, so things like video surveillance, IP cameras. And so basically some examples of some of the items you might use. All right, and so the management and automation pillar. So IoT expands the size and diversity of the network to include billions of smart objects that sense, monitor, control, and react. Each of these areas also has distinctive requirements, including the need to track specific metrics. Cisco management automation products can be customized for specific industries to provide enhanced security and control and support. So management tools, Cisco IoT Field Network Directors, Cisco Prime, Cisco Video Surveillance Manager, and more. So basically, the whole automation thing is why we have so many sensors, I suppose. So, I suppose you can imagine a farmer and, they're trying to save water. And so you can have a water sensor. It's a water sensor, a moisture sensor in the soil. And so they only water the fields when they need it. And so, and that can be automated. And so, that is just one tiny example of, millions of possibilities, basically. Now, cloud and virtualization. So, of course, cloud computing is a pay-as-you-go model where capital expenditures are transferred to operating expenses. And so instead of buying your own data center, so you got to set aside a room and secure it and air condition it and put racks in, and then all your devices, and then there's the electricity you got to use to run it, and there's all these things that you need to do. Many of them are up front, and of course you still do have ongoing expenses as well. Instead of having that capital expenditure to set it up, you just go to a vendor like Amazon or Microsoft or Google, and you pay them a monthly fee for whatever resources you need from them, basically. And so you can have a large number of network computers physically located anywhere. Providers rely heavily on virtualization, reduced operational costs by using resources more efficiently, and supports a variety of data management issues, and so enables access to organizational data anywhere and at any time. It streamlines the organization's IT operations by subscribing only to needed services, eliminates or reduces the need for on-site IT equipment, maintenance and management, reduces costs for equipment, energy, physical plant requirements and personal training needs, enables rapid responses to increasing data volume requirements. And so basically IT is going down the way that, I don't know, electricity generation went more than 100 years ago, where big companies used to generate their own electricity if they needed it. Now, of course, not many people do that anymore. And so now IT is becoming a service as opposed to a department. Now, cloud services. Cloud computing services defined by the National Institute of Standards and Technology, or NIST. And so there's sort of different levels of service. And so you've got software as a service. So basically you buy an email package or Office package or whatever it is, and it's delivered over the internet. And so be that Outlook or Word or whatever it might be, it's a service you can pay for, and it's software. That's I'm going to say there's computers, there's operating systems, there's all that stuff in the background, but you just care about the software that gets delivered to you. And so platform as a service is basically you're paying for a Windows or a Linux server or whatever it might be, and then you can put whatever stuff you want on top of that device. Infrastructure as a service is basically more bare bones hardware that you then can put your own operating systems or whatever it might be on it. And then there's IT as a service, where IT professionals support applications, platforms and infrastructure, and so that's sort of more complete than even software as a service. Now, when it comes to clouds, there's different models. And so there's public clouds where application services are made available to the general population. Services may be free or offered as a pay-per-use model, such as paying for online storage. It uses the internet to provide those services. And so, Google, you can if you've got a Google account, you can use a word processor, and you name it, you can do all that stuff on their website. Basically, you don't need to have Office installed on your machine. It may not necessarily be the the gold standard of thing, but hey, it's free and it's pretty good. So private clouds are where applications and services are intended for a specific organization or entity, such as the government. A private cloud can be set up using the organization's private network, though this can be expensive to build and maintain. A private cloud can also be managed by an outside organization with strict access security. So basically, the private cloud is quite similar to a public cloud, but it's just limited who can access it, basically. And so it may well be on your premises, or it may be administered by a service provider, but you've paid for it, it's yours. That cloud is yours. And so hybrid is basically where you have combined private and public clouds, and so basically it's just a combination, as the word hybrid suggests, I suppose. And there are community clouds. So a community cloud is created for exclusive use by specific community. For example, healthcare organizations must remain compliant with policies and laws. And so basically you can have a cloud that sort of runs in exactly the way that it needs to follow their legislation, basically. All right, so cloud computing versus a data center. And so, of course, a data center we think of our internal data center where you have your own servers and the like. But of course, you can lease it off-site as well. While with cloud computing, basically, it's off-premises that offers on-demand access to the shared pool of configurable computing resources. These resources can be rapidly provisioned and released with minimal management effort. And so basically, there's still going to be a data center, but it's not your data center. It's going to be Amazon's or Google's or Microsoft's or whoever it might be. And so you're still using a data center. It's just that you're renting a part of someone else's data center. Okay, so cloud computing and virtualization. And so virtualization is the foundation of cloud computing. Without it, cloud computing would not be possible, or at least be a lot more difficult. Cloud computing separates the application from the hardware. Virtualization separates the operating system from the hardware. So Amazon Elastic Compute Cloud, or EC2, is a web service and provides a simple way for customers to dynamically provision the computer resources they need. These virtualized instances of servers are created on demand in their cloud, basically. So, of course, with virtualization, you can actually have a dedicated server for each role that's required. And so it could be a web server, email server. You can have all these different servers, but of course, because they're not a separate piece of hardware, they're a virtualized entity. You can have all of these separate servers, but they can actually be running on, way less than, that's 8 servers there, but you wouldn't have to have 8 computers to run them on. So it does depend on what resources they've got available. But yeah, you could have 4 on each server if you've got 2 servers or whatever it might be. And so basically in the figure, the previous 8 dedicated servers have been consolidated onto 2 servers using hypervisors to support multiple virtual instances of the operating systems. So a hypervisor is a program, be that firmware or hardware, that adds an abstraction layer on top of the real physical hardware. The abstraction layer is used to create virtual machines which have access to all the hardware of the physical machines, such as CPUs, memory, disks, and NICs and the like. It is not uncommon for 100 physical servers to be consolidated as virtual machines on top of 10 physical servers that are using hypervisors. Okay, one major advantage of virtualization is overall reduced costs, because you don't have to buy as much equipment, and so you can do some server consolidation. So you might buy new equipment, of course, which is higher end with greater capabilities, and then you can combine, consolidate multiple servers onto that one piece of hardware. And so the less physical servers you're running, the less power you're going to use. So that again saves electricity and of course money. Less space is required, and so your data center doesn't need to be as big, so that's going to cost you less as well. And so there are additional benefits of virtualization, easier prototyping. So it's not hard to create a VM and have a play and see whatever you need to trial. And it's very quick and easy to do. So it's very fast to provision a new server. You've got increased server uptime, improved disaster recovery, and you've also got legacy support. So when it comes to disaster recovery, you can actually have VMs move from one server to another dynamically as either loads increase or maybe some hardware has a problem. Okay, so abstraction layers. So a hypervisor is installed between the firmware and the OS, and the hypervisor can support multiple instances of OSs. And so basically, this is how a normal computer runs. You've got your hardware, you've got some firmware, you've got the operating system, and then whatever services are running on that operating system. And so here, we've basically just added another layer in between, the hypervisor. And then on that, of course, instead of having one OS, you can have multiple operating systems, and they all can run services themselves. So there's 2 types of hypervisors. And so type 2 hypervisors are sort of the hosted approach, where you actually have an underlying operating system. And so here, you might have a Windows 10 machine, and you've installed VMware Workstation, or you could be using Virtual PC or whatever it might be, VirtualBox. And then on that, you can have, so this would be the host operating system, and then there would be, in this case, there's 3 guest operating systems, which are the virtualized operating systems. And so, Type 2 hypervisors are also called hosted hypervisors. This is because the hypervisor is installed on top of an existing operating system, such as Mac OS or Windows or Linux. Type 2 hypervisors are very popular with consumers and for organizations experimenting with the virtualization. And so, so it works well, and it's good for trying things out. So again, if you're an IT manager, you might just have one of these and try out your VMs on your personal machine, and then once you've tried it out, you can then actually migrate it to your active server as well. So type 1 hypervisors, they're often called bare metal, and so of course the hypervisor runs directly on the hardware, and so then it creates the environment for those multiple operating systems to be on. And so usually used on enterprise servers and data center networking devices. Instances of an operating system are installed on the hypervisor. Type 1 hypervisors have direct access to the hardware resources and improve scalability, performance, and robustness. So how do you install a VM on a hypervisor? With Type 1, you need to have, of course, have the hypervisor's management console, and the management software is used to manage multiple servers using the same hypervisor. The management console can automatically consolidate servers and power on or off servers as required. So assume that server 1 in the figure becomes low on resources. To make more resources available, the management console moves the Windows instance to the hypervisor on server 2. So the management console provides recovery from hardware failure. If a server component fails, the management console automatically and seamlessly moves the VM to another server. The management console for Cisco Unified Computing, or UCS, is shown in the figure. And so the manager controls multiple servers and manages resources for thousands of VMs. Okay, network virtualization. So server virtualization hides server resources from server users. This practice can create problems if the data center is using traditional network architectures. So for example, virtual LANs or VLANs used by VMs must be assigned to the same switch port as the physical server running the hypervisor. However, VMs are movable and the network administrator must be able to add, drop and change network resources and profiles. This process is difficult to do with traditional network switches. Another problem is that the traffic flows differ substantially from the traditional client-server model. Typically, a data center has a considerable amount of traffic being exchanged between virtual servers, referred to as east-west traffic. These flows change in location and intensity over time, requiring a flexible approach to network resource management. Existing network infrastructures can respond to changing requirements related to management of traffic flows by using QoS and security level configurations for individual flows. However, in large enterprises using multi-vendor equipment, each time a new VM is enabled, the necessary reconfiguration can be very time consuming. All right, so network programming. And so we're going to talk about the control and data planes here on the routers. I think mostly what we're talking about. Or layer 3 switches. So the control plane is regarded as the brains of a device, used to make forwarding decisions. Information sent to the control plane is processed by the CPU. The data plane, also called the forwarding plane, this plane is the switch fabric connecting the various network ports on a device. The data plane of each device is used to forward traffic flows. So CEF, or Cisco Express Forwarding, is an advanced layer 3 IP switching technology that enables forwarding of packets to occur at the data plane without consulting the control plane. Packets are forwarded directly by the data plane based on information contained in the forwarding information base and adjacency table without needing to consult the information in the control plane. And so basically CEF is, I think we did talk about this back in semester 2, CCNA 2. Is basically the router actually trawls through all its routing information and other such information, and then basically updates a database, that forwarding information base, and basically When packets arrive, it can actually look up that database and pretty much at wire speed forward the packets out where they need to go towards their destination. And so instead of having to go up through RAM and the CPU to crunch it, the CPU's done the crunching previously about conversations like that, and it's actually updated the switching basically to be able to do that at wire speed. Okay, so control plane and data plane. To virtualize the network, the control plane function is removed from each device and is performed by a centralized controller. The centralized controller communicates control plane functions to each device. Each device can now focus on forwarding data while the centralized controller manages data flow, increases security, and provides other services. And so basically, I suppose it's a bit like how many wireless networks are set up, where you have your lightweight access points, and then you have your wireless LAN controller, which actually tells them what they need to do. So virtualizing the network. So two major network architectures have been developed to support network virtualization. So there's SDN, or software-defined networking. So that's a network architecture that virtualizes the network. And then there's the Cisco Application-Centric Infrastructure, or ACI, a hardware solution for integrating cloud computing and data center management. These are some other network virtualization technologies, some of which are included as components of SDN and ACI. So there's OpenFlow, and so that's a protocol is a basic element in the building of the SDN networks. And OpenStack, this approach is a virtualization and orchestration platform available to build scalable network environments and provide an infrastructure as a service solution. Okay, so the SDN architecture, in a traditional router or switch architecture, the control plane and data plane functions occur on the same device. Routing decisions and packet forwarding are the responsibility of the device operating system. SDN is a network architecture that has been developed to virtualize the network. SDN can virtualize the control plane, and so SDN moves the control plane from each network device to a central network intelligence and policy-making entity called the SDN controller. And so that's basically the SDN controller there, and each of the devices have to communicate with it. Okay, so the SDN controller enables network administrators to manage and dictate how the data plane or virtual switches and routers should handle network traffic. So the SDN controller uses northbound APIs to communicate with upstream applications. These APIs help network administrators shape traffic and deploy services. The SDN controller uses southbound APIs to define the behavior of the downstream virtual switches and routers. An API is a set of standardized requests that define the proper way for an application to request services from another application. OpenFlow is the original and widely implemented southbound API. So application programming interface, of course, is what API stands for. So an SDN controller and operations. So the SDN controller defines the data flows that occur in the SDN data plane. A flow could consist of all packets with the same source and destination IP addresses, or all packets with the same VLAN identifier. Each flow traveling through the network must first get permission from the SDN controller. If the controller allows a flow, it computes a route for the flow to take and adds an entry for that flow in each of the switches along the path. The controller populates and switches, and the switches management the flow tables. Each OpenFlow switch connects to an OpenFlow to other OpenFlow switches. They can also connect to end devices that are part of the packet flow. To the switch, a flow is a sequence of packets that matches a specific entry in its flow table. Okay, so ACI. So three core components of ACI architecture are the application network profile, the application policy infrastructure controller, and the Cisco Nexus 9000 series switches. So the ANP is a collection of endpoint groups, their connections, and the policies that define those connections. So the APIC is the brains of the ACI architecture, a centralized software controller that is designed for programmability and centralized management, translates application policies into network programming. And then the switches provide an application-aware switching fabric and work with an APIC to manage the virtual and physical network infrastructure. So the APIC is positioned between the ANP and the ACI-enabled network infrastructure. The APIC translates the application requirements into a network configuration to meet those needs. Okay, so a spine leaf topology. And so we basically have, so the Cisco ACI fabric is composed of the APIC and the Cisco Nexus 9000 series switches using two-tier spine leaf topology as shown in the figure. Leaf switches always attach to the spines, but they never attach to each other. And so you can see these are the leaf switches here. Spine switches only attach to the leaf, and core switches not shown. So Cisco APICs and all other devices in the network physically attached to leaf switches. When compared to SDN, the APIC controller does not manipulate the data path directly. The APIC centralizes the policy definition and programs the leaf switches to forward traffic based on the defined policies. Okay, so SDN types. So to better understand APIC EM, it is helpful to take a broader look at three types of SDN. So there's device-based and controller-based SDN. So with device-based, the devices are programmable by applications running on the device itself or on a server in the network. Cisco 1PK is an example of a device-based SDN. It enables programs to build applications to integrate and interact with Cisco devices. With controller-based SDNs, they use a centralized controller that has knowledge of all devices in the network. The applications can interface with the controller responsible for managing devices and manipulate traffic flows throughout the network. The Cisco Open SDN controller is a commercial distribution of Open Daylight. Okay, and so the last one is a policy-based SDN, and it's similar to a controller-based where a centralized controller has a view of all devices in the network. It includes an additional policy layer that uses built-in applications that automate advanced configuration tasks via a guided workflow and a user-friendly GUI. No programming skills are required, and so the Cisco APIC EM is an example of this type of SDN. Policy-based SDN is the most robust, providing for simple mechanism to control and manage policies across the entire network. Okay, so APIC EM features. And so it provides the following features: discovery, device inventory, and host inventory, and policy. And there's topology and policy analysis. So with discovery, it supports a discovery functionality that is used to populate the controller's device and host inventory database. With the inventory, it collects detailed information from devices within a network, and including device name, device status, MAC address, IPv4 and 6 addresses, iOS and firmware, platform, uptime, and configuration. The host inventory collects detailed information from the host within the network, including name, user ID, MAC address, IP addressing, and network attachment point. With policy, it's the ability to view and control policies across the entire network, including QoS. Topology supports a graphical view of the network topology. And then policy analysis is inspection and analysis of network access control policies. The ability to trace application-specific paths between end devices to quickly identify ACLs in use and problem areas. Okay, so APIC EM ACL analysis. One of the most important features of the APIC EM controller is the ability to manage policies across the entire network. So the analysis and path trace provides tools to allow the administrator to analyze and understand ACL policies and configurations. The ACL analysis tool enables ACL inspection and interrogation across the entire network, exposing any problems and conflicts. With the path trace, this tool examines specific ACLs on the path between the two end nodes, displaying any potential issues. Okay, that's it for the chapter. So we've looked at the value of the Internet of Things. We've explained why cloud computing and virtualization are necessary for evolving networks. And we've explained why network programmability is necessary for evolving networks. So that is the end of the chapter. And so we've just got chapter 8 to go, and then that's it for the course. So have a nice week. I'll see you again next time. And stay healthy.